Swayam Prabha. Digital India. Educated India.
New lecture of fundamentals and applications of dielectric ceramics. So let's just recap the previous lecture. So in previous lecture we started our discussion on ionically bonded solids. So we talked about the energetics of ionic bonding, and then we looked at Pauling's rules, which are basically guidelines to facilitate the formation of structures which are primarily based on radius ratio and keeping the electrostatic repulsion minimum. And according to radius ratios, anions make certain polyhedra, and then cations occupy the interstices in them. So generally, as a thumb rule, when smaller the size of cation is, lower the number of neighbors there are going to be, which means the polyhedra is going to be smaller. And generally for bigger size cations, you have bigger polyhedras. And then we looked at structures. We started beginning to look at structures based on FCC packing of anions. So we looked at sodium chloride, which is rock salt based structures, and then we looked at fluorite and antifluorite structure. So fluorite is basically CaF2 kind of structure. So basically you can say AX2, and this would be A2X kind of structures. So A is the cation and X is the anion here. So next we look at now following the continuing the discussion on FCC packing of anions. The third structure that we would like to discuss is zinc blend structure. Zinc blend has a chemical formula of Mx, which means for every anion you have one cation. So stoichiometry is 1:1, and the examples of such these compounds are basically you have zinc sulfide, beryllium oxide, silicon carbide, gallium arsenide, gallium phosphide, many materials, especially these group 4 semiconductors, when they make compounds, and even 3,5 kind of semiconductors, they make these zinc blend structure. And generally this is followed in materials with covalent bonding, and where you have tetrahedral coordination of atoms. So here anions form the SCC lattice. So basically whether it's sulfur or oxygen or anything else, they form FCC lattice, and the cations occupy the tetrahedral interstices. And as a result, we can determine that only 50% of the tetrahedral sites are filled, because in FCC lattice you have, for every atom you have 2 tetrahedral sites, and stoichiometry is 1:1. As a result, only half of the tetrahedral sites are filled. And given the fact that the stoichiometry is 1:1, to satisfy the bond strength of cations and anions must be equal. The anions are also tetrahedrally coordinated. So the coordination of both anions and cations is tetrahedral, or 4-fold coordination. And the radius ratios for these kind of materials fall in this range. So 0.225 to 0.414. So zinc has 0.06 nanometer. You can determine all these radiuses and then determine the radius ratios. Sometimes there may be some off radius ratio structures which still show zinc blend, but that is determined more by the bonding than by the radius ratio. So it does happen in some cases, but by and large they do fulfill the criteria. So this is the kind of structure. This is very similar to covalent diamond structure, except that in diamond all the 8 sites, 4 FCC and 4 tetrahedral, are filled by carbon atoms. Here 4 FCC sites are filled by sulfur atoms, and 4 tetrahedral sites are filled by zinc atoms or any other cation. So these are all tetrahedrally coordinated cations, and these are all anions which make FCC lattice, but even anions are tetrahedrally coordinated. So both of them have tetrahedral coordination. So this is called as sphalerite or zinc sulfide structure. So this is a very simple structure. There is nothing very complicated about it. So sulfur also has 4-fold coordination, and zinc also has 4-fold coordination. And next we move on to what we call as a spinel structure. A spinel is a material which is spinel structured materials are basically Ab2O4 kind of materials. So here generally you have this kind of formula, Ab2O4, and this Ab2O4 is represented as A is 2 plus, B is 3 plus, and then remaining 4 are oxygen atoms. So there is one of A atom of 2 plus valence, there are 2 of B 3 plus, and then 4 oxygen atoms. You can also write this in such fashion, so that it's a mixture of two sublattices, one of AO and second is of B2O3. This is another way of representing this. So it's a mixture of two oxides, AO dot B2O3. This again is based on FCC packing of oxygen or anions, and in this structure you have partial occupancy of both tetrahedral and octahedral sites. You can see that you have 4 FCC, 4 oxygen atoms. So for 4 oxygen atoms you will have 4 octahedral voids and 8 tetrahedral voids, but you have only 3 cations. Okay. So the way it happens is you have 1/8 of tetrahedral sites which are filled. So which means out of 8 only 1 is filled, and out of 4 basically 2 are filled. Okay. So depending upon how cations arrange themselves in these interstices, it could be normal or inverse, but the filling pattern is 1/8 of tetrahedral sites and half the octahedral sites are filled, which make up 3 cations that are present in the formula. So basically what happens is that in a spinel unit cell, essentially you have 8 FCC unit cells. So you have 4 unit cells at the bottom, 4 unit cells at the top. So 8 into 4 will make 32 oxygen atoms. So for 32 oxygen atoms you will have 8 A atoms and 16 B atoms in the unit cell. This is how the unit cell looks like basically for a spinel structure. And then depending upon how cations occupy different interstices, whether tetrahedral or octahedral, the structure may be called as normal or inverse, and we will look at both the examples in a short while. Normal spinel structure is, again the chemical formula is same, it is A2 plus B3 plus 2 atoms of B and then O4. The examples which follow this structure, among ferrites it is zinc ferrite that follows this structure, because zinc has a tendency to go to tetrahedral sites. Otherwise many ferrites follow inverse spinel structure. But then you have aluminates and chromates which follow this structure normally. So magnesium aluminate and metal chromates, a variety of metals you can put in there, they all follow normal spinel structures. So essentially what happens in this structure is the A atom goes to tetrahedral site and both the B atoms go to octahedral sites. So this is how, so you can write this structure as A tetrahedral, B2, or let me just so A tetrahedral, B2 octahedral, O4. That is how you can write this structure. And again you can see only one atom goes to tetrahedral size, so 1/8 filling of tetrahedral and then half filling of 50% filling of octahedral sites. You can apply the bond strength rule to verify the stoichiometry as well as the coordination of oxygen atoms. That I will leave it to you as a home exercise. So and the inverse spinel structure is again the same formula, but it is conveniently written as BABO4. So essentially what happens here is the B atom goes to tetrahedral sites and one A and remaining B go to octahedral sites. That is how this structure is written as inverse. So it's one B goes to tetrahedral site, another B goes to octahedral sites and the A goes to octahedral sites. So here you can see that B divides itself into tetrahedral and octahedral sites and A goes to octahedral site. Most of the ferrites, with the exception of zinc ferrite, tend to follow this structure. So iron oxide, which is Fe3O4, nickel ferrite, cobalt ferrite, ferrite, etc., they all follow this inverse spinel structure. And depending upon the arrangement of, so all of these ions you can see, nickel, iron, cobalt, they all have magnetic moments. So depending upon their distribution in these tetrahedral and octahedral sites, they carry certain magnetic moment. So which is outside the scope of this lecture, but it's an interesting exercise to do for you. So essentially here half of the B plus ions occupy the tetrahedral sites and remaining B and all of the A occupy the tetrahedral sites. This is how the inverse spinel structure is. So this is the structure which is of AB2O3 type. This is basically taken from, let me just tell you, you can look at the details of this structure. So this basically it is adapted from a chemistry website, which is chem dot so it has some very nice structural illustrations. So you can go to this website and look at these structures, but it has been redrawn to so you can see that this is a one FCC cell, and within one FCC cell you have certain tetrahedrally coordinated atoms and some of the octahedrally coordinated atoms. So this is the first cell on top, then you have another cell on the back, so you have 8 cells on top of each other. So the all the atoms have not been drawn for the sake of simplicity, but for example, this is one oxygen atoms. So these are all oxygen atoms. Okay, so this is one oxygen atom which tetrahedrally coordinates these A atoms. Okay, and then so the lattice you can see is made up of A atoms, but I mean, if oxygen makes FCC lattice, then A and B will also make FCC lattices. So essentially that is something which they have to follow, otherwise it will not remain like a FCC lattice. So basically you will have 8 FCC lattices of oxygen. You will have, so it's AB2O4, right, multiplied by 8. So 8 FCC lattices of oxygen, you will have 8 atoms of A, so 2 FCC lattices of A, and you will have 4 FCC lattices of B. So each of these will make FCC lattice in itself. That is a crystallographic requirement for it to be FCC. So here you can see that these are A atoms, these are tetrahedrally coordinated. The B atoms are sitting here. So B atoms are sitting here. So you can see this is B atom. I have taken it out here. So this is B. You have one A here. You have another A here. You have another. This is oxygen. This is oxygen. This is oxygen. You will have one oxygen here. You will have another oxygen here, and you will have another oxygen here. So this will be octahedrally coordinated. So this is octahedrally coordinated B atom. This is tetrahedrally coordinated A atom. So this is, you can swap these positions depending upon whether it's normal or spinel, normal or inverse, but this is how the structure will be. It's a little complex structure, so you'll have to do a little bit of hard work to visualize it. So these are 4 basically most common structures based on FCC packing of anions. There are certain other structures where the structure looks like FCC or BCC, but it's not FCC BCC, it's based on primitive cubic arrangement. So for example, the first one is cesium chloride type of structure. Basically again it's a MX type of compound, 1:1 stoichiometry, and it's called as cesium chloride structure because the parent compound is cesium chloride. And there are many halides which follow this structure, such as cesium chloride itself, and then silver iodide, silver bromide, etc. All of them follow this structure. The radius ratio governs in this case. So RC by RA is such that it governs. So it is greater than RC by RA is greater than 0.732. So which means it governs. It must have. So basically cations are bigger in this case. So as a result, there is a cubic coordination of both cations as well as anions because of stoichiometry, and the lattice type is primitive cubic in this case, and the motif will be anion. So now if it's a primitive cubic lattice, so when you define the motif, you will have to define both the ions. The anions will be at 0, 0, 0, and cations will be at half, half, half. It's not a BCC structure because both the lattice points are different, and there is one formula unit per unit cell. So this is the structure like. So you have X atom sitting at the 0, 0, 0 kind of positions, and M atom sitting at half of half kind of positions. So this is a cesium chloride structure, which is, a lot of people conceive it as BCC structure, but in BCC structure the center and the corner atoms have to be the same. In this case it's different. That is why it's so you can consider this as a molecule of this and that. So basically one molecule is sitting on a lattice point. So it's a molecular structure with a primitive cubic lattice. The next very important structure in this series is perovskite structure, which many of the dielectrics follow, especially non-linear dielectrics, and these perovskites are basically AbO3 kind of compounds. So you have 2 cations A and B and 3 oxygen atoms, and there are plenty of examples of these materials such as barium titanate, strontium titanate, lead titanate, potassium niobate, bismuth ferrite. A lot of these follow these perovskite structures. In fact, many other materials which are not which do not have simple formula, even they tend to follow perovskite unit as building blocks. So, for example, materials such as Bi4, Ti3, O12, it is a very tall structure, but it tends to follow perovskite unit cell because perovskite units are present as building blocks in these materials. So, it might have multiple units of perovskites. So, these are very important materials because many of the perovskites are dielectrics and ferroelectrics and piezoelectrics. The radius ratio is such that A atom is bigger. As a result, A atom is 12-fold coordinated. So, which means it is a cubic coordination and 6-fold, it is a FCC kind of coordination, and then B atom is 6-fold or octahedrally coordinated in this case. So, B is the smaller one, A is the bigger one. So, for example, if you look at barium titanate, barium is big and titanium is small. So, this has 12-fold and this has 6-fold, and here oxygen atoms form a FCC like cell. It is not a FCC cell, it looks like FCC, but it is not FCC because the atoms, there is no atom at the corner of the unit cell. So, for the sake of simplicity, the way it is represented, oxygen atoms are present only at the face centers. So, the way the structure looks like is something like this. You can always apply the bond strength to satisfy the chemical stoichiometry and charge neutrality. So, what you have here is these yellow ones are oxygen atoms. So, all the oxygen atoms occupy this face centers. So, ideal structure is a cubic structure, but really speaking most of them are not cubic in especially in the ferroelectric state. So, these oxygen atoms occupy the face centers. The titanium occupies the body center, which then becomes octahedrally coordinated by oxygen atoms, and the barium atoms go to the corner. So, as a result, this although looks like face centered cubic kind of structure, but it is not face centered because the corner atoms are different to face centers, and then it is also not body centered because body center atom is different. So, as a result, this is a primitive cubic lattice. It is a primitive cubic lattice, and you can also represent this structure in a little differently. If you put the lattice corners at titanium, then titanium becomes the corner atom. In those cases, barium comes to the center, but then oxygens are distributed in such a fashion so that oxygens are present at the edge centers. Okay. So, edge centers will become oxygen atoms. So, basically it is like this. If you put your corner here, so you will have one direction going like this. So, this will come to edge center. Okay. So, that is why you can construct the lattice. So, it is like you can see that these are all octahedras which can at the center of whose you have titanium atom, and then within the center of these 8 octahedra you have this titanium barium atom which is surrounded by 12 of oxygen atoms. There are 12 edges, so 12 of these oxygen atoms, it is surrounded by 12. So, this is the simple perovskite structure. It is followed by many technically important ceramics. So, the way you define lattice type is, it is primitive cubic lattice, it is not FCC. So, as a result, the motif is A is at 0 0 0, B is at half of half, and oxygen is at half of 0 0 0 0 half half and half 0 half. You will have to define all the positions for a primitive cubic structure. So, basically it is a molecule, right. One molecule is sitting at one lattice point. So, you have one formula unit per cell, that is why one formula unit is one lattice point, okay. And coordination is B is surrounded by oxygen octahedra and A is surrounded by oxygen dodecahedra, which touch faces of the octahedra. And these perovskites are not only AbO3 kind of perovskites, they can also be mixture of cations of different types. So, not only you have BaTiO3, PbTiO3, etc., you can also have A3B3 kind of combination. So, A3 plus B3 plus. So, in this case you can have lanthanum aluminate, you can have gallium lanthanum galliate, bismuth ferrite. So, here you can see the valence of cation is 2 plus and 4 plus. In the second case you have 3 plus and 3 plus. So, this is 2 plus 4 plus and this is 3 plus 3 plus. You can also have mixed perovskites such as A2 plus and B atom can be mixture of 2 plus ion and 5 plus ion, such as lead magnesium niobate. It is a relaxer material. Similarly, you can have a mixture of, so basically it is a solid solution of, you can say which the B solid solution in such a fashion so that B site is partially doped by 2 plus or 5 plus atom, okay. And then we have we can have A2 plus, B3 plus and B5 plus in the stoichiometry of half-half. So, you can have lead, scandium, tantalate kind of materials. So, variety of these materials have these partial substitutions of sites by different ions. Of course, you will have to maintain the stoichiometry in such a fashion so that it remains charge neutral, but mixed perovskites are there. These are all, they have different properties as we will see later on in the ferroelectric in the material section. One of the important things that we need to know about the perovskite structure is the tolerance factor. Tolerance factor is basically sum of radius of A ion plus oxygen ion divided by root 2 of sum of B cation radius and oxygen radius, and you can see that very clearly. This is very simple to derive. You can see that this is what is R of 2RO plus 2RB, right, okay. And if it was a cube, what would this be? This would be 2 of RO plus square root 2. So, this will be basically this is equal to A, and A root 2 will be equal to square root 2 of RA plus 2 of RO, and then you can just eliminate A. And so, for ideal material this ratio should be equal to 1, you are just equating the A, okay. So, that is how you find out tolerance factor. So, tolerance factor will be 1 for a perfectly cubic perovskite, but if it is not cubic, which it is not in most materials, it tends to deviate from 1. Generally it tends to be lower than 1, but generally you have tetragonal distortion or rhombohedral distortion. So, and this cubic structure changes to tetragonal at room temperature, for example, for barium titanate. So, many of these materials have transition temperatures. Above certain temperature they are cubic, and below that temperature they are non-cubic structured. So, we will see that when we learn about the ferroelectric materials. And then there are other materials such as yttrium, barium, copper oxide, bismuth, titanate, etc. All of these are based on perovskite based structures, but so you can look at them in any book on. So, this is for example yttrium, barium, copper oxide, which has these units of perovskites staggered on top of one another. So, I will skip this for the sake of time. So, let us move to now next final part of this, that is HCP packing of anions, where anions pack themselves in HCP fashion, and the cations occupy the interstices. So, the structures that we will consider are woodsite, corundum, ilmenite, lithium niobate and rutile. Many of them are similar, but we will see how the deviations take place. So, woodsite is basically a compound with mx stoichiometry, m is to x is equal to 1 is to 1. The materials which follow this structure are basically zinc sulphide, zinc oxide, silicon carbide, etc. So, again zinc sulphide, zinc oxide, etc. they also follow cubic structure, and the polymorph structures follow this woodsite hexagonal structure. So, here anions form HCP lattice with half of the tetrahedral sites filled by cations. So, again it is tetrahedral site filling, but in hexagonal form. And here anions pack in the form of AB, it's not ABC, ABC, it's AB sort of packing, and tetrahedral sites are occupied by the cations. Coordination of both anions and cations by stoichiometry will has to be similar. So, as a result it is 4, and it is similar to what we saw in sphelerite structured compounds. So, this is what the structure will look like. You have this is the first layer of X atom, there is a second layer of X atom. So, this is X, this is X, this is X, and the tetrahedral sites in between them are occupied by cations, but only half of the tetrahedral sites can be filled, not all of them, because for each ion you have 2 tetrahedral sites. So, if you make a unit cell in this, the unit cell will look something like this. So, you have these oxygen atoms sitting at the lattice sites, and then in between them. So, this is a tetrahedrally coordinated metal, this is a tetrahedrally coordinated metal. So, you have metals here, then another metal there. Okay. So, 2 cation and 2 anion will be what in a will be what that will be present in a lattice. And if you look at the plan view, this is how it is going to look like. You will have cations at position. So, these are the orange one are anions at 0 1. You have another anion sitting at the half position right in the middle of the unit cell, but then you have cations sitting at positions 5 by 8 along C axis and another cation sitting at 1 by 8. So, 5 by 8 minus 1 by 8 will be 1 by 2, right. So, there is displacement of half. So, just like you have this atom displaced from this atom by half, this atom is displaced with respect to this atom by half. So, you can construct a FCC lattice, HCP lattice by putting corner at the green atom rather than at the, so 0 position can be at the green atom instead of orange atom, because it is HCP lattice. So, both M is also HCP and X is also HCP lattice. So, if you look at the ZNO structure, the first layer will be this zinc oxygen hexagonally, then zinc atoms go to 1 by 8 sites, not all of them, but only half the sites are filled. Then again second layer of oxygen atom, and then again another layer of zinc atom which goes somewhere, then another layer of, so you have another layer of zinc atoms, another layer of oxygen atoms, and that is what makes a unit cell. This, the red one is the unit cell which will contain these oxygen atoms and the zinc atoms. Okay. The corundum structure is now Al2O3 kind of structure, M2O3 it is called as. So, basically it is alumina based, parent compound is alumina, but there are other materials such as iron oxide, chromium oxide, variety of A2O3 kind of structures, they follow corundum structure. Here oxygen makes a HCP lattice and metal goes to octahedral sites. Okay. Now, since for each atom you have one octahedral sites and the stoichiometry is 3, which means only 2/3 of octahedral sites are filled, okay, because you have 2 cations for every 3 anions. And as a result, because of stoichiometry, cation has 6-fold coordination because of radius ratio, and because of bond strength the anion will have 4-fold coordination, right, because cation has a very 3 valence, coordination is 6, and the bond strength of anion has to be same as this. So, which means anion is 2, which means it has to be 4-fold coordinated. So, this is the coordination number of anion. Okay. And since stoichiometry is 2:3, the octahedral site filling is 2/3. So, this is the structure. The way it is formed is you make first layer of oxygen, then you fill in octahedral sites 2/3. Okay. So, you can see for every 2 one is empty, then this octahedral site will move to another position in the next layer to maintain the periodicity of the lattice. So, the next oxygen layer goes like this. So, you can see that this is octahedral. So, 3 inverted and 3 up facing oxygen atoms. The second layer will go like this, then the next layer of, so it has to complete the triangle to make a repeatable lattice. Then the third layer of oxygen will come, then you have another layer of oxygen, then you have vacant octahedral site again, and this structure. So, you have to repeat this once more to get a repeatable lattice. So, this whole structure consists of 6 layers of oxygen. Okay. And the way you visualize this structure is, it's if you look at, for example, cross section of this 10 plane, put in first layer of oxygen, then you put in second layer of aluminum, one is empty, another layer of oxygen, another layer of metal, again one empty, and you keep doing this, do it 6 times, and this is what you get. So, you can see that for every 2 atom, of every 3 atom, the third site is empty, and it has to go in such a fashion so that it follows a pattern like this. Okay. So, these are basically, you can say, the arrows which are pointing to columns of phase sharing octahedra. So, basically these are the octahedral positions. You can make another structure based on the same thing, which is ilmenite. Ilmenite is AbO3, but it is not perovskite. Essentially it is Al2O3, but instead of 2 aluminum you have 1 A and 1 B, same as Al2O3, but you have divided 2 aluminum into 1 A and 1 B. parent compound is FeTiO3, which is called as ilmenite mineral. That is why it's called as ilmenite, but there are a lot of other materials, cadmium titanate, cobalt titanate, etc., which follow similar structure, and then they make this. And the atomic arrangement is similar to Al2O3, but the difference is, instead of aluminum being in every layer, you have alternate layers of iron and titanium. So, in one layer you will have iron, second layer you will have titanium, then iron, then titanium, and then you keep continuing like that. And the coordination numbers remain same, both iron and titanium remain octahedrally coordinated. So, the way this structure goes is, you have first layer of oxygen, second layer of iron, again the same fashion as aluminum, and again you put in the second layer of oxygen. Okay. Now you put second layer which is of titanium. Okay. Then you put again second layer of iron, oxygen, and you keep continuing this few more times. So, again you continue for 6 times, basically 6 layers, and you will get a structure. So, this is how it is going to go: iron, oxygen, titanium, iron, oxygen, iron, titanium, and so on and so forth. So, this, the way you do this structure is like this. So, you have, this is the titanium layer, iron layer, 1 empty, this is the titanium layer, 1 empty, this is the iron layer, 1 empty. So, you can see that it has to go progressively in this fashion. Even this way you can see iron, titanium, iron, titanium, iron, iron. So, it is alternatingly coming in every direction, and this is basically similar to Al2O3 structure, except that now you have 1 layer of iron, 1 layer of titanium. And the next variant of this is, again it is the same thing. Again another variant is lithium niobate, which is similar to the alumina structure, except that in the previous case we had 1 layer of iron, then titanium. Here you will have in the same layer alternating lithium and niobium atoms. So, the way this structure goes is, we will see in the next slide, but this is a material which is very important, lithium niobate. Lithium niobate is a ferroelectric. It is also it is a birefringent material. It has highly anisotropic refractive index, so it is optically very important material. So, it is a birefringent material which is, and this refringence can be changed by electric field. So, in this material we have oxygen layer, then we have second layer where we can consider, so you can see this is lithium, this is niobium, this is empty. The second again oxygen, then again you follow, so again you will have, sorry if I, so this is how it will be. You have lithium, niobium, empty, niobium, empty, lithium, empty, lithium, niobium. This is how you go. So, now you have alternating atoms in same layer. This is what the this is what is lithium niobate, and here, since you have these lithium niobium atoms stacked in this fashion, they also form these dipoles. These are permanent dipoles, and these, all of these dipoles, they point in the same direction. So, this is lithium, this is niobium, there is a charge density difference. So, as a result you have dipoles pointing in this direction. So, this is basically a ferroelectric material because of permanent dipole moment. Finally, so and this is how it looks like if you look at the top view. This is the oxygen layer, and these are all octahedrally coordinated. So, this is lithium, niobium, lithium, niobium, lithium, niobium, and this site is empty in the middle. So, these are empty channels, these are filled channels. So, these are filled channels of, so this is filled channel of niobium, filled channel of lithium, empty. So, you can look at this in various ways, but again you have to maintain the 2/3 filling. And finally, we look at rutile, which is a polymorph of titanium dioxide, which is very important material. It exists in anatase and brochide forms also, but rutile is the most commonly used material, and it is also again based on HCP packing. So, it is based on HCP packing, but it is not quite HCP, it is slightly distorted, that is why it is called as quasi HCP packing. So, what happens here is, again here half of the octahedral sites are filled by cations, because you have 2 of the oxygen atoms. So, only 1 cation, so only 50% can be filled. The resulting structure, because the distortion happens to be tetragonal instead of hexagonal closed packs. And this material is very important because it have anisotropic diffusion properties of cations. So, as a result, it has several technological applications. It has large anisotropic refractive index. It also has high birefringence. So, this is how the structure looks like. You have this hexagonal sort of arrangement of oxygen atoms, and titanium goes to tetrahedral, octahedral side. So, you can see that this one channel of titanium is filled, second is empty, third is filled, fourth is empty. So, only 50% filling is there, and when you stack it all together, the structure looks something like that. So, you make a cell, you can keep the corner at the titanium atoms. So, one corner will be here and then another will be at the center, and the oxygen atoms will be like this, and they make a octahedra, which is not a regular octahedra, slightly distorted octahedra. And if you want to look at the polyhedral picture, it is like this. You have 8 octahedras facing in this direction, and you have this octahedra facing in this direction. Slightly distorted structure, that is why it is a tetragonal instead of hexagonal close packed. So, this is where we end with this structure of ceramic materials module. We looked at FCC and cubic based ceramic structures, which consist of sodium chloride, zinc blende, fluoride structured materials, spinels, cesium chloride and perovskites. Not all of them are dielectrics, but many of them happen to be dielectric, especially the perovskite structured compounds, they happen to be dielectric in nature. And then we looked at HCP structured compounds, which are basically woodsite, corundum, ilmenite, lithium niobate and rutile, and many of these materials are dielectric in nature. Titanium oxide based materials are dielectric, ilmenite, lithium niobate are dielectric materials. So, this is a sort of summary of how the structure of these ceramic materials, dielectric ceramics evolves. I hope you've got a fair idea of how the structure of these materials is like and how is it derived. And in the next lecture now we will take up the defect chemistry of these oxides, which is important from the perspective of determining their properties. So, thank you very much. This is a summary slide which you can read for yourself. So, thank you.